a lot of pressure to compress it, but it's compressible. But a lot of pressure means a lot of depth of water. If you don't have a huge depth, you can assume that the fluid is incompressible. Perfect. Then we can apply the continuity equation, which is given by this one. You start from here. This is the first step of the Laplace equation, where u and w are the component of the velocity vector along the two spatial coordinates. This is the continuity equation, and you have to learn it by memory. There is no way, or there is way of deriving it, but I don't suggest you to study it. So just learn it by memory. It's very simple. And I will not ask you to learn many things by memory, by the way. And now, we assume that the motion of the fluid is irrotational. There is a link if you are interested, but I'm not telling you follow this link, because this definition just rely on your comprehension of what irrotational means in practice. Okay? And take into account and tell me, if I ask you the question, that irrotational means that we can write the velocity as the partial derivative of a potential phi. The potential, when we can write the velocity component as the derivative, partial derivative of a potential for any time, it means that the fluid is irrotational. And then you substitute this expression for u and w into the continuity equation, and you get the Laplace equation. That's it. And this is the Laplace equation. So I may ask you how to get the Laplace equation, and then you just have to say, first we assume that we are dealing with a plane wave, and then we write the continuity equation. The continuity equation with respect to an assigned control volume, you don't need to specify what it is, it's a generic control volume, and then you, by memory, write this equation. And then you say, this continuity equation applies under the assumption that the fluid is incompressible. Okay, then you tell me, we assume that the flow is irrotational, which means that we can express the component of the velocity vector as the partial derivative, first derivative of the potential. And then you write down these two relationships, you just substitute and you get the Laplace equation. You see, there is just a substitution of the component of the velocity vector there. Very simple. Now, the problem is that this is a partial differential equation. So, we are interested here, actually, in describing what? In describing the velocity. Because we are not interested in describing the potential. Laplace equation gives us an equation for the potential. We resolve the Laplace equation, we get an expression, an explicit expression for the potential. Once the potential is known, we derive the potential and get the velocity. So this should be clear to you. When you look at the equation, don't make the mistake that I did when I was a student. I just learned the equation and say, okay, this is the Laplace equation. And I didn't think about what is the meaning of the equation. Try to keep in mind what is your meaning. Your meaning is to define the velocity vector of a wave. Because you need to know the velocity with which the wave approaches the beach. because then you estimate the erosion, you will see. We will estimate the amount of beach erosion on the basis of the knowledge of the velocity vector of the wave. Okay, so in order to describe the motion of the wave, keep in mind that you need to describe the velocity vector. And therefore, what is the reason why you started the potential? You write an equation for the potential because you need to estimate the velocity vector, and you know that under the rotational assumption, if you take the derivative of the velocity, you estimate the derivative of the potential, you get the velocity vector. Okay, this is the first thing to take into account. Second thing, okay, I understood that I need to describe the potential in order to compute beach erosion, to estimate beach erosion. Okay, that's fine. But differential equation, what does this mean? Now, we don't have to go back to mathematics, but I know that you as an engineer, as I am, we are all concerned by a differential equation because we like an explicit equation, an equation that gives us the value of the design variable depending on some independent variables. A differential equation doesn't give you the explicit value of the potential. It gives to you the value of a change in the potential. Now, keep this into account because we don't associate often the meaning of the term differential equation to the fact that it just describes the change in the variable instead of the variable itself. We are interested in the variable. The differential equation, it has this problem. It doesn't describe the variable. It describes the change in the variable, change with respect to space, x and z, or with respect to time. So, what do we need to do once that if we want to get the value of the variable, we have to sum the changes, and this is the integral. So once that we, in order to solve the differential equation, solving the differential equation means to compute the value of the variable. And given that the differential equation gives to me only the change, I need to sum the changes, and this is the integral. Now, we are very concerned by integrals because we think it's a difficult story, but it's nothing else than a sum of the changes. Okay, so let's get used to it, and let's get rid of our concern. Now, the problem is that if you just sum the changes, you still don't get the value of the variable, because you need a starting point, a starting value. Do you understand this? So you sum the changes, you need a starting point. The starting point is the initial and boundary condition. So, when we listen about differential equation, I need to give initial and boundary condition. Oh my God, what is this? It's nothing else than giving the starting point in order to compute the sum. And with the advent of the personal computer, this is very clear, because I mean, we are allowed to transform the integral in a summation in the personal computer. When we make a program, this is what we do. Numerical integration. It's just a sum. And the sum is the simplest of the mathematical operation that we can do. And we need a starting point, initial and boundary condition. Okay, so to solve this equation, you need to specify the initial and boundary conditions. You don't have to learn this. I don't ask you at the exam what are the boundary conditions of the Laplace equations, because they are a bit difficult. But let me just recall you, okay? And I will not ask you. Let me just recall so that your colleagues that didn't study this, they can understand, okay? So, we can specify, first of all, there are several initial and boundary conditions that you can specify. And depending on the kind of initial and boundary condition, which is a starting point again, then you get a different solution. Typically, what we do is to assume that the sea bottom is impermeable. There is no flux of water through the sea bottom. This is a reasonable boundary condition. But of course, we may also impose a different one. But this is typically what we impose. Okay? Now, there are two boundary conditions at the water surface. The first one is called the kinematic boundary condition. And the kinematic boundary condition at the sea surface is obtained by imposing that there is the fluid particles that are close to the surface remain close to the surface. So there is limited movement of fluid from the surface to the deep part of the wave. Let's forget about the mathematical description of this. It's a bit complicated. It's a bit complicated because you don't know where the sea surface is. So you don't know the spatial coordinates where you have to specify this boundary condition. This makes the problem really complicated.
Sorry, could you repeat again? Mutated?
Sorry?
What is the kinematic boundary condition?
Okay, so let's suppose that you have a wave like this. Let me try to reach a better mark. You have a wave like this, and you have the sea bottom. Okay, so first boundary condition, no. Okay. You have no transfer of fluid through the sea bottom. Fine. Now, let's suppose that here you have a fluid particle which is close to here. And you impose that this fluid particle remain at the same distance of the surface, remains on the surface, okay? The fluid particle that is on the surface remains on the surface. Actually, this is not true, because if you remember, and if Professor Marchetti told you, there is, in the proximity of the surface, there is a movement of sea particles, a circular movement of sea particles, of fluid particles. So we can impose that they remain very close to the surface, and this is the kinematic boundary condition. But the problem is that while the sea bottom, you know the coordinates and stays there, the surface, you don't know the coordinates. They depend on the solution of your equation. So this makes the problem very complicated. It makes it nonlinear. Now, second boundary condition, it's the dynamic boundary condition, P equals 0. So atmospheric pressure at the surface. This is a dynamic boundary condition. It's called dynamic because it has to do with forces. Okay, now, if you translate this condition in mathematical terms, you have the means to move forward with the solution. And again, mathematical description, let's forget it, okay? So you have the mathematical problem, you see it there, that is written in conclusion. The mathematical problem is defined by the following equations. And the first one is the Laplace equation, and then you have the three boundary conditions. Okay, now of course the solution is to be computed.
For what concerns the third boundary condition, we are assuming a time condition. I mean, it's the initial condition, and we assume a certain point in time in which we are start to studying our problem.
Yes.
Our volume, our portion of volume.
Yeah.
And how is defined there the time? I mean, which is the meaning of that initial condition?
Okay, we are not specifying any initial condition here because basically it is something that you have to define. It's not defined here, and you need it indeed. So basically, you need to define also this boundary condition. You see that they all depend on time, yes. And therefore you either specify a boundary condition that is constant in time, so it's steady condition. Or otherwise you have to give a boundary condition as time 0, which is your initial condition. Okay, and it's basically it's implicit here because the boundary condition also depends on time. Okay, and you know the initial condition sometimes the effect of the initial condition vanishes as time goes on. So basically,
it depends, of course, from the partial differential equation.
Yeah.
Maybe is there some initial condition, some boundary condition that depends on time,
Yeah.
and some boundary condition that not depends on time.
don't depend on time. But in this case, I would say that the sea bottom, you may say that it's impermeable. So actually, the first one I think could be given in the form of it's 0 at any time. Yeah,
Not
it's
depend on time because
Yeah.
the boundary condition in time remain the same
Yeah,
because it's impermeable.
yeah, it's impermeable. Yeah. Okay, so now, just for your information, usually we solve the problem according to the linear theory. What is the linear theory? The linear theory is obtained by assuming that the boundary condition of the surface are given at a fixed spatial coordinate, which means that you give them at the average sea level. This resolves the problem of the lack of knowledge of the position of the sea surface. So basically you give a boundary condition that doesn't depend on the solution of the equation, and you give it at the average sea level. This is an approximation which is of course more acceptable if you have a small amplitude of waves, and it implies the superimposition principle, and it's called linear for this reason. What does this mean? If you have two waves that get together, the resulting wave is given by the sum of the effect of the two individual waves. So the linear theory implies the superimposition principle, which means that if you have two wave forcings, you obtain the total forcing by just summing the two individual waves. It means that, for instance, amplitude is given by the sum of amplitudes. It means that the velocity vector is given by the sum of the two individual vectors. Now, the linear theory is a commonly accepted assumption, but in particular situation where you clearly recognize that the wave is not plane, for instance, or you clearly recognize that the wave has a very important amplitude and therefore the assumption may be very weak. In some cases, even the laws in force, even the technical guidelines may suggest you to make reference to the nonlinear theory. It's a significant complication. I talked once with a professor of coastal engineering, very experienced, that told me you have to look at the sea. If you look at the typical wave forcing is clearly close to plane, and the wave can be clearly recognized with an amplitude that is not very relevant, then that's fine. And he told me, if you instead see that you cannot recognize the waves, you see a lot of turbulence, you see a lot of waves interacting, creating turbulence, then the linear theory becomes an approximation that is not really very good. But just keep in mind that the linear theory is a simplification that is classically and frequently applied. And keep in mind, I may ask at the exam what is the linear theory, and you just have to tell me the boundary condition at the surface is given at a fixed coordinate, which is the average sea level. That's it. Okay, then there are the possible solutions, and we focus on regular waves, namely waves with constant amplitude, period, and direction. This is the kind of wave we will focus on because it's the first approach. It's the first approach in coastal engineering. Okay, and the solution has the form that you see here. The potential is given by a sinusoidal equation of which depends on a wave number, a frequency, and phase. I'm not interested in these details. I will not ask you at the exam. Okay. Okay. And let's forget about this. Phase velocity, wave properties. Here there are a lot. There is a table with several wave properties, but let's forget about this. Now, this is what concerns the mechanics of sea waves, and I just would like to remind you, we don't need in this introduction to coastal engineering to look in details at the mechanics of sea waves. You just have to remember what are, for our interest, the main behavioral wave that we need to know. So, the wavelength, the wave amplitude, which is not shown here, I would say. You understand the amplitude is the difference between the highest and the lower level of the wave. And keep just in mind that we need to know this. Amplitude and length. This is what is relevant for our, and the direction. The direction of the velocity vector. This is what's relevant to us. What's relevant? Just look at the terminology. What is the crest? What is the through? The crest is the highest point, the through is the lowest one, and the period, what is a period, what is the frequency? And these terms, just learn them. And just keep in mind that if you didn't attend, if you attended the course with Professor Archetti of Ocean Engineering, you know this. So you know enough. If you didn't attend the course, just keep in mind that you are moving forward now in a simplified context where you don't know really the fundamentals, the basics of mechanics of sea waves. Just keep it in mind as something that if you need or wish to go in more details, is something that you have to learn. I also tell you that my webpage is probably not the best way to start. And, but it's not an easy subject. So I don't have any suggestion to you to tell you, look at another reference which is simple. You know, it's not an easy subject. But just keep in mind that we don't strictly need it, but because this is a basic treatment. If you need more information, just start from this. Okay? I think that's it for now.